Welcome back to another fun episode, a Q&A episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I'm your host, Heidi Campo, filling in for Andrew Dunkley, and joining us is Professor Fred Watson, astronomer at large. How are you doing, Fred? That was quite the smart little adjustment of your glasses. It made you look even more smart.
Oh, thank you, Heidi. You can come again. Look, it's great to see you again, and all going well here, and lots of exciting space stuff always to talk about, especially with the questions that we get from our listeners, which are always intriguing and often very insightful.
Yeah, and so we have 4 questions today. Two audio questions, 2 written questions. But we do want to say, if you did not hear our announcement on the last episode, we'll make that announcement again. We just want to say thank you to our listeners. We were declared, I guess you could say, the 7th top 7 astronomy podcasts, wherever you listen to your podcast. So thank you so much. Fred, do you have anything you want to add to that?
Only that it's amazing how many people do listen to our podcasts. I was in a medical waiting room on Monday, and a gentleman, I think his name was Stephen, came up and said, "I really enjoy the podcasts."
Oh, wow.
So
That's
it's quite nice.
You're like a celebrity.
Well, you must be too. I bet you find people, and if you don't now, you will do eventually. People who come up to you and say, "Yeah, I know your face," or "I know your voice." Yeah.
Well, I think I have to leave my house for that to happen. I'm too busy. I'm at the lab or I'm at home, so you don't see me in public unless you see me at the grocery store.
There you go. That could be where it happens. You never know. So anyway, yeah, it's great to have that 7th ranking in the world's top 50 astronomy podcasts. I'm thrilled to hear it.
Well, I guess that makes our regular people who write in their questions famous too then, because we do have some regulars, a few of them today. Our first question today is from Mark Painter. And Mark has another black hole question. And then he has this funny emoji next to it that he made with text. It's not like a regular emoji. He did that with like special characters. Very clever. All right, so we have another black hole question from Mark. And Mark asks, as a singularity is formed with infinite mass, there must be a process of reduction, starting with electron degenerate matter, then collapsing to a neutron star. Then there is a quark matter in massive neutron stars where quarks are no longer confined to protons and neutrons. So my question is this: can there be more stages of matter reduction to go through before a singularity or a Planck star is formed? That is, can quarks be composed of smaller units of matter and then these units break down to their constitutes and so on? Could there be many forms of matter we are yet to theorize and at some time possibly discover? Could it be elephants all the way down?
Yeah, turtles all the way down. I think that was the other way of looking at the universe. So it's a great question. If you think of, so we envisage the process of a black hole forming after a supernova explosion. You've got the star which has run out of hydrogen fuel. This is one way of black hole formation. There's others. But anyway, it runs out of hydrogen fuel, so there's no longer the outward radiation pressure to support the mass of the star, and it collapses. And if there's enough material there, the collapse doesn't just stop with as Mark points out, electron degenerate matter. That's what we call a white dwarf star. Or it doesn't stop with that, and it doesn't stop with neutron degenerate matter, which is what we call a neutron star. It just collapses down basically to to a singularity, to this point of infinite density. It's not infinite mass, as Mark said, it's infinite density. But that's not the point. The point is, is there, as you get to that singularity, are there other constituents of matter that the collapse goes through? And my understanding of this is that the answer is no. We understand very well from particle physics what the most fundamental particles of matter are. And it's what we call the Standard Model. There are 16 of them, plus something called the Higgs boson, which gives all the others their mass. And these, as far as we know, are indivisible. They are not able to fall into pieces. They are the ultimate, the ultimate building blocks of matter. There are 6 quarks: the up, down, charm, strange, top and bottom quarks. That's the quark component. So quarks themselves have different varieties. There are 6 leptons: the electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. And then the 4 fundamental forces of nature, what are called the gauge bosons: the gluon, which operates the strong atomic force; the photon, which we know is all about electromagnetic radiation; and the Z and W bosons, which dictate the weak nuclear force. So those are what everything is made of. And the idea of separating them into smaller particles, I think, is something that the particle physicists rule out. They're telling us that that's the way it goes. And so, yes, as the collapse takes place, these are probably the last things to not to come into existence, but to disappear down the singularity, if I can put it that way. But it's a great question, Mark, and got me thinking about particle physics once again.
Excellent. Well, it looks like our next question is from one of those famous regular listeners, and it is a audio question. So we are going to play that for you now. You guys can all listen to Buddy from Oregon's question, and Fred and I are going to listen to that right now. I'm just letting Fred get that queued up. All right, everyone, we're going to play Buddy's question for you now.
This is Buddy from Ontario, Oregon again. Hey, I was listening to your latest episode, and where you announced that there's a third object from outside our solar system passing through a comet, I guess. And I know you said there was no point before in trying to catch these objects, because if you can get that fast, you can sense something or that object in any direction. What if you were to just land like a spin launch on one of those objects with a few satellites? That way, anytime it happened to get close enough to something interesting, we could launch it with a spin launch and possibly maybe use that spin launch to counteract the speed that you're going at, so that you could just kind of gently place a object in orbit around something. Seems like we should have eyes in every direction we can send one. But anyways, what do you guys think? Thanks, guys. Love this podcast.
Intriguing stuff from Buddy, as always. So just filling in a few gaps in that. Spin launch is indeed a technique for launching space vehicles. It's a company, I think they're called Spin Launch. And they've built this gigantic device that spins things up to a high level of rotation, and that lets them go. My understanding, although they've got, I know there's an announcement recently, they've got a large contract for some possible space vehicles. I don't think they've yet achieved a sufficient velocity as you release it from the spin to get into orbit. That needs to go up to 8 kilometers per second, and I think they're much less than that. So from Earth, that's not really a viable way of doing what Buddy's talking about, which is chasing after an interstellar object. if you had one of these machines on board a spacecraft already, that might be a viable way of doing it because you only need to give it a smaller impulse. But you can still do that chemically. You can actually, you've got much more control over what you're doing with chemical rockets. And the problem is, as Buddy highlights, the objects like these various, the three interstellar objects that have passed through the solar system, Oumuamua, Comet Borisov, and the current one, 3I Atlas, which is showing all the signs of being a comet. That one's passing through the solar system at the moment. The problem is they're moving so fast. Atlas is moving at 60 kilometers per second. It's a huge speed, bigger than anything that we've ever launched into space before. So we'd never chase it. And this is the problem from our vantage point on Earth. The idea is that one of these things comes in, you mount a space mission to go and rendezvous with it and check it out, which would be wonderful. But exactly as Buddy says, you need eyes in all directions. And more especially, you need spacecraft that are probably already out there, just waiting to be deployed in particular directions. Now, there's an interesting footnote, though, to this story, because within the last week, we've had a proposal from our good friend Avi Loeb of the Harvard-Smithsonian Center for Astrophysics. He has made the suggestion that because the Atlas comet currently going through the solar system from some other solar system, it's probably older than our solar system, because that passes relatively close to Jupiter, and I think it's either next year or the year after, I think it's probably next year, you could deploy a spacecraft already in orbit around Jupiter, and he's thinking of the Juno spacecraft, which is already orbiting Jupiter and telling us a lot about that planet. You could change its orbit. It's in a already in a highly elliptical or elongated orbit. Loeb and his colleagues suggest that you could change that orbit, make it elongated enough that you actually get a closer look at Comet 3I Atlas as it passes by Jupiter. And that would be fabulous because it would be a way of getting up close and personal with an interstellar object that might tell us a lot more about it than we know already. So I think this is an exciting area that Buddy's highlighted, the idea of rendezvousing with extraterrestrial or extrasolar asteroids or comets, rendezvousing with them with whatever we have at our disposal. And if we've got Juno at our disposal, already hanging around in the vicinity of Jupiter, maybe it will be a good thing to do to bring the mission to an end by rendezvousing with Comet 3I Atlas. So I like that question.
A lot of tongue twisters in this field.
Yeah, it's true.
Hi, everyone. Let's take a moment to talk about our sponsor, Insta360, the trailblazers in 360 and action cameras, pushing the boundaries of what's possible for creators everywhere. Last week, Insta360 dropped their latest game changer, the Go Ultra, a pocket-sized camera that's redefining how you capture life's adventures. Imagine a camera no bigger than an Oreo, weighing just 53 grams, yet packed with the power to shoot buttery smooth 4K video at 60 frames per second. It's small enough to slip into your pocket, but delivers professional-grade footage that'll make your vlogs, travel diaries, or family moments look absolutely stunning. What makes the Go Ultra stand out? The standalone camera is IPX8 waterproof up to 33 feet, so whether you're surfing, swimming, or caught in the rain, it's ready to roll. The Go Ultra's upgraded sensor and AI chip ensure your shots are crisp and vibrant, day or night. And if you misplace your camera, Apple Find My Compatibility has your back to track it down. Here's the best part. For the first 30 Space Nuts listeners who purchase the Insta360 Go Ultra at store.insta360.com, you'll score a free sticky tabs accessory to mount your camera on anything from backpacks to winter jackets. Just use the promo code SPACENUTS at checkout. That's store.insta360.com, promo code SPACENUTS. Check the description for links and more details. Don't miss out on this tiny titan of a camera that's ready to capture your world like never before. Now, back to the show.
Roger, you're loud and clear here also.
Space nuts.
Our next question starts off with a tongue twister. This is Lawrence from London. Says, "Hiya, gents. Lawrence from London. Lawrence from London here. I will jump straight to the point. Has there ever been any sort of proposal of space-time being a superfluid? And if so, how did that play out? One of my biggest grievances are those space-time diagrams that show a single plane with the planet on top causing curvature on said plane. For me, it feels like it skews the four-dimensional reality that truly exists, as there is not just a single plane for everything to rest on. If we could find ways to visualize this more accurately, I feel like we would appeal to the fluid more often to describe the behavior of space-time, as it would allow for these extra dimensions rather than the typical two-dimensional space-time diagrams. As for time, perhaps it could be understood to be the flow rate of the superfluid. As for the elasticity and the structural integrity we see of space-time, maybe quantized vortices? As for gravity, I have no idea. It is a good thing that I can ask this question to an astrophysicist. Many thanks, gents. Looking forward to hearing your response." I'm interested, too. That was quite an interesting visual.
Yeah, that's right. And his point's well made. Thanks, Lawrence, for this. Your point's well made that we have no way of depicting space-time being distorted by matter, which is what happens, other than, this picture that we all are familiar with of a planet sitting on a trampoline, with the trampoline mat being distorted by the gravity of the planet. That's because we have to reduce it to two dimensions. It's because it's the only way we can really envisage it. But the notion underlying Lawrence's question is that he's sort of, in a sense, ahead of the game. And that is because, he talks about superfluids. A superfluid is a fluid with zero viscosity. And that is what space-time is. It is already effectively a superfluid. Our understanding of space-time comes from general relativity, Einstein's general theory of relativity. And he understood the idea that matter would distort space, because he was basically trying to understand gravity. And he basically, what he did was propose that gravity was the way he was approaching this. Gravity is the same as acceleration. So if you were in a spacecraft with no windows, and somebody lit the fuse and put the rocket underneath the spacecraft and sent it accelerating on its way, from within that spacecraft, you would not know whether you were feeling the effect of the acceleration or the pull of gravity. They are indistinguishable. It's something that technically is known by the equivalence principle, which holds up incredibly strongly. So what you're saying is gravity and acceleration are effectively the same thing. That allowed Einstein to build a geometrical model of how gravity works, and that's what led to our understanding of space-time, something that is distorted by the presence of matter. It's got a gobbledygook description. The mathematical description, or the mathematical structure, if you like, that we see as space-time, it is based on geometry developed by a German mathematician can't remember his first name. His second name was Riemann. Riemann, in the 1850s, proposed the idea of spaces that could be distorted by things within them. And that turns out that that's exactly what space-time is in the relativistic view. It's a mathematical construct that we call a Riemannian manifold, and it is a superfluid. It basically behaves just like a superfluid, and the quantized vortices that Lawrence mentions, that puts a different slant on it because you're suddenly into quantum theory rather than relativity theory. So we'll just leave that to one side. But as far as relativity is concerned, space is a superfluid. And the way gravity emerges, Lawrence says, as for gravity, I have no idea. It's a good thing I can ask this question to an astrophysicist. Well, I'm glad you did, because gravity is the acceleration. It's the distortion of space causing us to feel an acceleration, which we see as gravity. I hope that answers Lawrence's question.
That was fantastic.
3, 2, 1.
Space nuts.
Our very last question of this episode is from Dan on the Gold Coast. And this is also an audio question. So I'm going to give Fred just a second to cue that up. And we are going to play that for you now.
Hey guys, Dan here from the Gold Coast. Quick question, thought it might be a bit different for you. Got a friend who a couple of years ago we were discussing space exploration and that kind of stuff. And his view was that he'd understand why the human race puts time into exploring space when we still don't quite understand Earth. And I couldn't put into words myself why it's so important, which I understand it is. I was hoping you could put into your own words, why is it so important that we also put time into exploring space? Thanks for that. Also, Heidi, with your sci-fi brain, I'm wondering, have you read Project Hail Mary? Do you love it like I do? And are you excited for the movie? All right, cheers. Bye.
Oh my goodness. I'm so excited that you brought up Project Hail Mary. That is next on my list. It is next on my list. I have read other books from that author and I'm very excited to read it, but I have not yet. And I feel a little bit like a hypocrite because I pride myself on often reading the books before the movies, but now I feel like a hipster because I'm reading it before the movie comes out.
That's good. No, you're ahead of the game, Heidi. That's the great thing. When you've read it, I'd love to hear what it's about.
It's a space book.
Yeah. Yep. Sounds great. Very quickly, why do we explore space? Why explore the universe when there's so much on Earth that's left to understand? And I guess one way of there's many reasons why, and it's principally governments that support the exploration of space, certainly by astronomers, and to some extent the exploration of space by space probes as well, although there's certainly a commercial sector moving into that, trying to send spacecraft to the moon and things of that sort. But why do we do it? Well, we wouldn't be able to understand Earth fully if we didn't know about space. So the two are really part and parcel of the same thing. It's trying to understand our environment on the biggest possible scale. And if you didn't understand how planets form, then it wouldn't really tell you how the Earth has formed, and that's an important part of the Earth's history. So that's and of course the other thing is that we as a species are curious. We want to know about our environment in space. We want to know about the origin of space. We want to know about where everything came from. It's fundamental science that may not have an immediate commercial benefit, but it tells us about ourselves and satisfies our curiosity, our yearning to understand the scale of space and how it all works. That's I guess, the fundamental reason for doing it. But there are many other reasons. One reason why governments invest in space and astronomy is to inspire upcoming generations, because we know that there's nothing like black holes or killer asteroids or whatever for getting kids switched on to science. And it's a great way, even if they don't become astronomers or space scientists, they at least understand the scientific method. They understand the evidence-based method that is fundamental to all science. And so that's another reason. We've got, of course, spin-offs. We've got all kinds of things. There are 3 different things inside this mobile phone that I'm holding up. For those of you who don't have the YouTube version of this podcast, 3 things of that came from astronomy and understanding physics. The GPS system relies on general relativity, which was tested by astronomical observations. The camera in it was essentially evolved from cameras that were developed from astronomical cameras that we were bringing to fruition in the 1980s, these silicon devices that let us see very faint light levels, and Wi-Fi. The Wi-Fi that lets us use our phones actually started off in the head of an astrophysicist working in radio astronomy. How do you send signals backwards and forwards in your laboratories? And he was an Australian. Well, he still is. His name is John O'Sullivan, and I've had a number of pleasant chats with him over the years. Very well-known astrophysicist. So there are lots of reasons why we do space, not just because we are curious about it, but that's the main underlying reason.
Fred, what got you interested in space? Why did you choose this as a career?
Yeah, look, in a sense, I'm a product of exactly what I've just been talking about. Although things were a little bit different when I was a youngster, because I was at school in the late 1950s, early 1960s, at the dawn of the space age. So it was in our faces all the time. And plus the fact that there had recently been a world war, and a lot of people thought there was going to be another one, which will be fought on the grounds of science. So science was absolutely hammered into us. The school I was at had 4 streams. 3 of them were science streams, 1 was an art stream. And that is not the case now. So in a sense, I was a product of my time, but I was inspired by, in fact, an astronomer who I was only thinking about him this morning, sadly now no longer with us, a gentleman by the name of Patrick Moore, who was the most famous astronomer in Britain for 40, maybe even 50 years. He had a TV program which he started in 1957. It's still running. He's not does it anymore. The Sky at Night. So The Sky at Night was one of the things that inspired me and got me interested in space. And I never really grew up. I just carried on being interested and have been all my life. So
I love that. That's a really fun story.
Yes, I just feel very fortunate to have had a job throughout my life that I probably would have done even if they hadn't paid me for it, because it was my passion. Not sure how I would have lived had that been the case, but anyway.
That's wonderful.
It's been great.
Well, on that positive note, keep dreaming, everyone. Keep looking at the stars and keep sending us your questions. Especially if you're one of our female listeners. I have been here all summer and we have not gotten one question from the ladies. So if you're a female listener and you have been wondering if your question's good enough, it's good enough. Just send it in. We love our fellas, but if there are, we've got to have female listeners. This can't be 100% guys who are interested in space. So send in your questions. We want to hear from you. Fred, do you have any closing remarks?
No, just to say, absolutely, I agree with that. We do know we've got some female listeners. We've occasionally had questions in the past. We have one person who is a pilot. She flies across the Atlantic and looks at the stars and sends us notes about what she sees.
Oh, that's such a beautiful picture.
Yeah, isn't it great? And so, I agree. We should shout out to our female Space Nuts listeners. Get your questions in. We'd love to hear from you.
All righty then. Well, you heard it from the man himself. And you probably maybe only a few more weeks with me. So send in your questions that if you have any sci-fi related questions about favorite sci-fi books and whatnot, because Andrew is going to be back soon. We're not quite sure when, but we've got a few more weeks left with me, and then Andrew will be back as your host. But till then, you're stuck with me, and I thank you all for listening. Till next time, see you later.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.